All right, so let's start with 4.83. Racquetball is struck in such a way that it leaves the racket with this speed in the horizontal direction. When the ball hits the court, it is horizontal distance of this from the racket. Find the height of the racquetball when it left the racket. Oh, this is like almost identical to one of the example problems. Oh, you want me to pass it up? Okay, I'll do that. Let me just pause the recording. All right. I don't know why it's not happening that one. All right, so in this one, very similar to one of the example problems we did. 4.83. Not required, but I might do a diagram just to make sure my thinking is aligned. I would put things like the ball only has horizontal initial velocity. Ball is a projectile. The vertical motion controls time. That'd kind of be the base that I would need down here. Those ideas. And of course, by the ball as a projectile, what I mean is it's only influenced by the force created by gravity. Thus, the only change in its motion is it accelerating downwards, with the acceleration caused by the force due to gravity. But I might draw my little diagram here, giving my V initial in that direction, and then kind of just scoping out the path that follows. I know it's accelerating down at that acceleration caused by the force of gravity. Let's see, mine goes out. Mine is hit with 4.83. 83 meters per second. Mine lands 1.96 meters away. And they want to know this height here, which maybe I'll call H. All right. So, as with our other projectile ones, I'm going to divide my paper in half, with time being in between, and I'll do vertical over here and horizontal over here. And horizontally, both these I'm going to use, say D equals D naught plus V initial T plus 1/2 AT squared. Leave out my deltas just because it's Monday morning. And then looking at that horizontally, I'm going to call where the ball starts horizontally, I'm going to call that 0, and the ground right below that 0 also. So right below where it starts for me is going to be 0, 0. I'm going to take up and to the right as positive. So I'm going to end up at 1.96 meters equals 0 plus 4.83 meters per second times t. And then the whole 1/2 AT squared, of course, is 0, since I never have an acceleration horizontally. Solve that for t. Pull out my calculator at this point. Now, while the vertical motion controls the time, that's what decided how much time this had to move out horizontally. So I'm kind of working backwards here. So I get a time of 0.4 0.05797 seconds. That's what can hop the fence here into the vertical motion. Vertically, I'd start at that point. D equals D naught plus V initial T plus 1/2 AT squared. Where am I going to end up? 0. Where did I start? H. My initial velocity was 0, so that whole term goes out since I only had horizontal velocity. 1/2 downwards, negative 9.81 meters per second squared. T squared, I get the T from the other side. Solve for H. So for me, I get 0.808 meters. And let's see how many sig figs the problem asks for. All right, so 4.88. Chunkin, Sussex County, Delaware. Founders to build cannons. Have you guys ever seen this? Is it? Oh, that's right. I have seen that. But there's actually Discover, I think, did a show on this and followed some of the designers. Some of it is just really, really interesting how they do it. I never knew there was a catapult just powered by twisted rope till I watched that. All right, been projected 1,200 meters in the time. Now, when they say projected distance, they're talking about the horizontal range, not the distance along the path, but the horizontal displacement. So what is the minimum initial speed needed for such a shot? And do we have to answer that part before we can do other parts? Yes. So I'll do back. Or there's only one part to it, right? All right. So minimum initial speed, that comes back to one thing hopefully that you picked out of the videos or out of the readings, I know it didn't come up in class, is about maximum range. That the maximum range, in that we mean horizontal displacement, of a projectile that lands at the same height it is launched is when it is launched at 45 degrees. So when they ask for minimum velocity to maximize the range, what they're in kind of code-wise, they're telling you is that it was launched at 45 degrees because that'll maximize your range. The range is symmetrical around 45 degrees. So if you launch it at 0 degrees, 0 range. 90, 0 range. 45 maximum. And then they actually pair up with that symmetry around 45. Only if it lands at the same height that it's launched at. If it lands below or above, then that changes that. But, so, that would be the main thing in the why. I would say, you know, yeah, the pumpkin is a projectile, things like that, all those fun things. And then I'm going to do just a diagram down here to remind myself. And I'm doing 1,200 meters. I think that's what mine was, right? Yeah. All right. So first thing I need to do take that initial velocity that I'm looking for, VI, and separate it into horizontal and vertical parts. I know from my Y that this is 45 degrees, right? Oh, if that's 45, what does it mean about those two sides? Right, they're the same sides, because you guys know a 45, 45, 90 is an isosceles triangle. Yeah. Wow. So this side is VI cosine 45 degrees is actually the exact same as write it correctly, as VI sine 45 degrees. Right? Those are exact same values. So, what do the two dimensions share in common? Anybody? Time, right. Because every time we do two dimensions, what do they share in common? Time. Wow, good morning. It's Monday. Coffee is our friend, or tea, or hot chocolate, or whatever. Something. Good night's sleep is our friend. And so as much time as this pumpkin has to move horizontally, it has that exact same amount of time to move vertically. So let's do the vertical first. This should be in red. Just changing up my format in case some people don't like the two-column format. You're welcome to use it though. D equals D naught plus V initial T plus 1/2 A T squared. Let's see, the height that it lands at, 0. The height it starts at, 0. Its initial velocity, positive VI sine 45 degrees, T plus 1/2. The projectile, so negative 9.81 meters per second squared, T squared. Solve for T. What did I do with my calculator? Oh, wait a minute. I can divide every term by T, can't I? Oh, wait a minute. Can I solve that for T? I can, though, but I'm not going to get a numerical answer, right? Right? But if I divide each term by T and then solve, I get negative VI sine of 45 degrees over 1/2 times negative 9.8 meters per second squared. Right? Now, that doesn't give me a numerical answer because I don't know what VI is, but it does let me solve for T. And since T is common between both sides, that may allow me to bring the two sides together. So I'm just going to write this in a way that make an algebra teacher a little bit happier. 2 VI sine 45 degrees over 9.81 meters per second squared. And now let's go horizontal. Green was horizontal, right? And look at what is it doing horizontally. I know, shocking that I'd use that equation, right? Let's see, horizontally, it's going to end up for me at 1,200 meters. It's starting at 0. Its initial velocity is VI cosine 45 degrees. Time plus 0. I have the same two unknowns, VI and T. I could substitute in there, couldn't I? Let's try that. Let's substitute in the red into the green. We'll do that in blue. So I would end up with 1,200 meters equals VI cosine 45 degrees times 2 VI sine 45 degrees over 9.81 meters per second squared. Oh, now I can solve for VI, right? Just do a little algebra. So let's see. And I get and I get, what was that? I get 1,800. Sure. I isolated VI. I'll do it over here with simple numbers, okay? So I have that 5 equals x times 3 times 2x times 3 over 10. Okay? So to get the 10 on the other side, since it's on the bottom, I've got to bring it up. To get the 3 on the other side, I've got to bring it down. The 2 on the other side, I've got to bring it down. And the 3, I've got to bring it down. So I end up, because remember, to get across an equal sign, I have to do the opposite function. And sorry, oops, I wrote this wrong. This is b squared. So I have 5 over 3 times 2 times 3. That 10 came up, so that's times 10 equals, and then x times x is x squared. That's how I did it. Anything up top, I brought down. Anything down, I brought up. And so then I would get that B is, for me, 108 meters per second. So this would be meters squared seconds. Let's see if that works. All right, let's look at number 12 here. Swim directly across a river. And you got the swimmer that aims so he can swim directly across a river that has a downstream current of this. Now, on especially these river problems, you want to be conscious of the wording. So he aims so that he can swim directly across the river. That means he aims so that his path ends up being directly across the river. All right? That doesn't mean that he aims directly across. He aims so that he can swim directly across. So in diagram sense, if we, let's see, we'll treat this space as our river with the velocity of the river with respect to the bank or the current direction is down. That would mean that our swimmer is going to aim in this direction velocity of the swimmer with respect to the river, so that the velocity of the swimmer with respect to the bank ends up being directly across. As we add together, we add in here the velocity of the river with respect to the bank. When those add in, then you get an outcome of the velocity of the swimmer with respect to the bank. All right. So you could put some words in there. You could also just do a nice vector diagram on this one to show that you understand it. I'm going to call this angle theta. So word-wise, what I would probably add in there are things like velocity and displacement are in same direction always. And the velocities combine vectorially. And that's shown by the diagram here. So if his velocity ends up being directly across the river, his displacement will end up directly across the river. So let's see, what do they want to know? They want to know what must his direction be degrees upstream from straight across. Well, that's good. That's the angle. So they're asking for the angle I labeled theta. That's nice. And all right, so we want to look at this angle. Let's see. Still water, 5.54 meters a second. So that's going to be the magnitude of his velocity, the swimmer's velocity, and the current's magnitude for me is 3.38. So I'm just gonna redraw my triangle over here and draw it as a geometric figure rather than a vector triangle. Notice I've dropped the arrows. Remember, on that vector diagram, you have to have the arrows. This is still theta. This 5.54 meters per second, 3.38 meters per second. It's a right triangle. So opposite over hypotenuse will give me sine. So I can write sine of theta equals my opposite, 3.38 meters per second, over my hypotenuse, 5.54 meters per second, and find out my theta. Of course, by doing inverse sine, right? Or arc sine of those two. And I get 37.6 degrees for mine. That would be part A. In part B, they want to know how long it takes to go across the river. Oops. They want to know how much time will the swimmer spend getting across the 263 meter wide river. So I know that this is the triangle I've drawn here is my velocity triangle. I could draw an identical displacement triangle. And so I could use any of the displacements. They're all going to share a common time. The only one I know is the one directly across the river. But I know the triangle, this is a similar triangle. So this is 37.6 degrees. This base of it is 263 meters. I've got lots of options. I could find the side opposite the angle and then know that that displacement is created by the velocity of the river with respect to the bank. I could find the hypotenuse and know that that displacement is due to the velocity of the swimmer with respect to the river. Or I could find the velocity of the swimmer with respect to the bank, and then I know this displacement is caused by that velocity, all with the exact same time. So it's really up to me which one I do. I'm going to do the hypotenuse here. I'm going to figure out D and figure out the time it takes the swimmer in that direction. And so my D using trig will D over, see that's adjacent, so that's cosine of 37.6 equals 263 meters. It's in my problem. It tells me the distance across the river for me is 263. What does it tell you your distance is? Oh yeah, you gotta look at part B. It's in part B. What did they tell you though? What was yours? There you go. Okay. And so I can find. Wait a minute, that's not right. Let's see. No, sorry, I put that in wrong. I forgot my. So cosine must be Monday morning equals adjacent 263 meters over D. Oh, I did do it right. So D times the D equals 263 meters over cosine of 37.6 degrees. Once I find my D, which for me is, of course, I'm going to avoid rounding, right? So I'm going to use my calculator to my advantage. I get a D of 331.9374172 meters. I'm going to use D equals D naught plus V delta T from the top of our equation sheet, right? And use it 331.937 equals 0 plus, what was his velocity? For me, velocity of the swimmer 5.54. Delta T. Solve for delta T. I get 59.9. Let's see. Let me see.